Okay, hi everybody. I can't see you, so I'm going to have to engage reaction from how I normally receive reactions from these slides. I'm Jason Leigh, professor in computer science and also director of Electronic Visualization Lab. So thank you for inviting me to speak here. I know you guys are running late and probably missing lunch and all that kind of stuff, so I'll try to be brief. Before I begin, I just want to say a few words about the lab. In the next slide, the Electronic Visualization Lab, established in 1973, is actually the oldest institution in the United States that combines art with computer science. We have 6 full-time staff and we have about 15 funded graduate students. We began as art and computer science, but we've grown significantly to incorporate a number of collaborations in biomedical sciences, communications, engineering, and so forth. We're primarily funded by the National Science Foundation, but we also get smaller pockets of funding from other for-profit or non-profit organizations, such as the one you see here. One of the things, in the next slide, one of the things that we're best known for is for the computer graphics for the first Star Wars movie in 1976. So that was our earliest education and outreach effort. We trained the Rebel Alliance how to blow up the evil Death Star. And if you ever come visit us, we can show you an original piece of the Death Star that was used in the movie. Another thing we're known for is something called scientific visualization. We essentially invented the term in 1987. And basically it means to turn scientific data into images to produce insight. The next slide shows something called the Cave, which is a virtual reality system that we invented in 1992. This is a giant room, about 10 foot cubed, where you can walk inside and 3D images appear to materialize as if they were actually real. And so one of the early adopters of this technology is General Motors. So let's begin. Let's talk about big data in the next slide. So you've all heard the term big data. And in fact, if you look at any companies that are out there today, if they're not thinking or working or thinking about how to deal with big data, they're probably not going to be successful companies in the future. Because everything from automobile design, drug design, understanding climate change, understanding how a forest fire is going to burn in a certain direction, all involves trying to make sense of big data. And there's so much of it that, in fact, we are now drowning in it more so than we ever were. So part of the solution, and this is shown in the next slide, is in what we hope is an effective way of addressing it, which is basically visualization, which means to convert data into images for insight. Now, this is particularly relevant, especially the word insight, because vision is the primary means by which humans absorb information from their environment. And half of your brain is actually dedicated to processing visual information. So if you're not using visualization to try and understand the data, then you're really not using half of your brain to try and solve the problem. At least, that's sort of my take on it. And next slide shows that, in fact, computer displays are now becoming the modern lenses for examining scientific, engineering, and medical data. And so in the past, when we were kids and studying things like astronomy or biology, we would look through optical telescopes and microscopes. Today, sensors gather all this data, and the scientist and the engineer are primarily using advanced displays to try and make sense of this data. In the next slide, what I'd like to show is that, well, we firmly believe that the quality of the lens can really determine the quality of the insight. And so this fun example I'd like to show is Lowell, basically Percival Lowell, who created the Lowell Observatory in Flagstaff, Arizona. And through that telescope, he drew pictures of Mars, and you can sort of see his sketch of what Mars looked like. And so Mars had these nodes with these lines between them. And based on that, if you hit the space bar, he hypothesized that these were actually irrigation channels created by intelligent Martians. And this has sort of stuck with us since 1895, even in popular movies such as Total Recall. And in fact, it took us about 70 years. So in the next slide, NASA sent Mariner out to Mars to take pictures, and it actually took us 70 years to prove that Percival was essentially wrong, because at the time when Percival was taking these pictures, he really didn't have a good enough lens to take those images, and now we finally do. And so the quality of the lens really determines the quality of the insight. And I'll explain why that's important in the kind of work that we do a little bit later. But let's back up a moment. And so let's go look at, in the next slide, let's get some examples of how everyday humans who are not high-powered scientists try to make sense of the data. So here's a picture of somebody's office. This is actually an English novelist. He crafts really complex, detective stories. And what he does, if you go to his website, he's plastered all the four walls of his office with little Post-it notes. And he's using this essentially as a way to fuse all this information together to write the novel. In the next slide, you can see some pictures taken about, 8 years ago now, I think, from the Antarctic drilling program. So these guys go out to Antarctica and they drill pores into the ice, and they slice them apart, and then from that they can sort of see the history of the planet and how climate change might affect it. And so what they used to do was essentially scan all this data, all these cores, and then print it out on paper and run them down their office and have someone on the floor scrolling, crawling, and making annotations with a pen. So this really wasn't that long ago. This was, I think, around 2005, yeah. And this was considered sort of the state-of-the-art as far as National Science Foundation core drilling science was concerned. So clearly there's room for improvement. The next slide shows that companies are also a bit behind in the sense that, for example, this is a BMW, which is obviously one of the premier makers of automobiles. They have something called the Inspiration Wall, where they've got pictures plastered on the wall of fashion architecture. And so this is how BMW figures out sort of the trends in that they should be following when they're designing their future cars. The next slide shows the merging of Northwest and Delta Airlines. So here you essentially have a giant sheet of paper that they put on the wall, and again, lots of colored Post-it notes where they write little items to indicate on a timeline when certain events have to happen in order for this merge to be completed within a certain amount of time. And lastly, in the next slide, you'll see a picture that you would typically see in most movie studios. This one in particular was taken from Walt Disney Company, and oftentimes they have these things called war rooms or project rooms where teams come together, and all four sides of these walls are usually covered with images and documents all relevant to the project that they are working on. And you can see it, the director there is Zack Snyder, who directed the most recent Superman movie. This is how he basically does reviews. of the progress of his team. And so what can you sort of learn from these, present day, analog approaches to things? Well, in the next slide, I'll give you a few tips. First of all, when people work with big data, they like to spread all this information out. They like to organize information in a variety of ways. For example, spatially. They like to link between the pieces of information. They like, teams. They like to bring in teams so that they can solve big problems together. Because it's not just one person who has all the expertise. The knowledge is actually in all the team members. And they like to make the results of their collaboration persistent so that later on you can refer back to why certain decisions were made. And so we thought, if you look at the next slide, we thought, well, how do we begin to think about transitioning some of this technology to computer-based solutions? And so if you sort of look at this wonderful picture, this is Al Gore in his office, and you can see it's sort of this giant mess on his desk, and then the three large computer monitors in front of him. I mean, it's pretty obvious that the analog world is completely unmanageable as far as big data is concerned, and in fact, most of Al Gore's work is done on those three computer monitors. And this kind of trend is going to continue for scientists and engineers, and someday even artists. So, in 2000, moving on to the next slide, in 2000 we began to do some research in how we can use these information displays to create the kind of richness that you saw in those paper-based environments, and to hopefully someday replace it. In 2004, in the next slide, we received some funding from the National Science Foundation to build this giant 100-megapixel wall. And here you can actually see faculty and students gathered around the wall, and they're pushing their laptop screens directly onto the wall. And we started doing this as part of our every regular technical research meeting. We stopped using traditional projectors and so forth. This was the much better way to go because we're now able to present multiple pieces of information simultaneously on the wall. And then to support all this, we use a piece of software called Sage, which is a scalable adaptive graphics environment. And so I'm not going to spend too much time explaining this other than to say that it's open source and it's available on that website. We heard recently from National Science Foundation that it's very likely we will continue to get funding to support this for the community. So that means Sage will continue for about another 5 years. And at the same time, we have just licensed the technology to a company who will also help in providing technical support for production users. And NSF has been very supportive of this transition to the commercial space. So let me give you an example in the next slide of what it's like to work with Sage. So we're going to hit the animation key. And there's no audio that's relevant here, so I'm basically going to talk through it. So what you're seeing is our Cyber Commons, which is like an 8,000 by 2,000 pixel screen. It's got a giant touch screen on top of it. And one of our PhD students just brought up Sage, and now he clicked one of the menu buttons, and he's opened it up, and he's loaded some of the content onto the wall. And so, like a giant iPhone or iPad, you can manipulate documents on this wall. And so here, most of the documents that he's maximizing and minimizing, sort of going through all the little gyrations of what the system can do. Here he's tiling. Yeah, the documents can be images, they could be PDF files, they could be potentially spreadsheets, some of them could actually be even 3D images. There are a couple of different gestures that you could use to do things like minimize the screen, minimize the content, bring it back up. You can create organizational panes, so like dividers for different parts of the wall, so you can move and adjust things and all the content automatically resizes. Now, where Sage gets exciting is in this context, where you're having a meeting with multiple collaborators. They all have their laptops open, and everybody has control of a pointer, of their own pointer with their name on it. So they can manipulate any of the content, any of the windows on that screen. Not only can they manipulate it, they can take any document that's on their laptop and drag and drop it onto that screen for everyone to see. They can also push their laptop screen directly onto the wall so that there you see, I think a push just appeared on the wall of somebody's laptop screen. And so you can see all this activity is happening in parallel. And this is really how you want to take advantage of these kinds of big wall display environments. Allow people to work in parallel so they can maximize the amount of work that can get done. And this mode of operation now has become so routine that we use it in all our the classes that we teach. I teach, for example, software design. And when the students have to do code review, they will have one part of the screen covered with the documentation, another one with source code, another one with execution run. And so it really changes the way students work together in teams. Here, for example, is Professor Andy Johnson, who teaches a class in data visualization. And here, the students can actually do their homework assignments and then post their attempts at interpreting some data onto the screen so that they can compare and contrast between them. So this is almost like the kind of stuff that you used to do when you were kids and your teacher asked you to pin up the pictures that you drew for homework on the back of the room so that everyone can see it and discuss it. Except, we kind of all forgot that when we grew up and went to college. But this is actually bringing it all back, and it's an incredibly engaging way of teaching. So Sage, the software that drives this, has been ramping up quite dramatically. In the next slide, you can sort of see the current adoption rate of Sage. We have, in 2013, over 100 display walls deployed, and all running the Sage software. In some cases, we're finding that institutions are starting to build multiples because the utilization has gotten so high. So if I were to drill down just a little bit in some of these wall systems, in the next slide, remember the poor chap in the Antarctic drilling program who was on the floor writing notes? Well, there's a happy ending to that story. We began working with them soon after, and so now all their digital core data is accessible from high-resolution display walls and computer screens so that they can make annotations directly on the screen. So this was so successful that the team brought 5 of these systems to Antarctica during one of their expeditions so that as they were drilling the cores, they were able to look at them, annotate them, and then while they're there, discover whether they had to drill more cores because some of their data had gaps. And it's extremely expensive to fly in and out of Antarctica to do science, so you may as well get it right the first time. And so this kind of ability of examining the data as quickly as possible is incredibly important too. So walls have continued to spread, and some organizations have built really extravagant, enormous walls. This one, for example, at the Texas Advanced Supercomputer Center is one of the highest resolution in the world, with 300 megapixels. It was paid for by oil company money. That's why the force is so big and all-encompassing. This is interfaced directly to a high-speed network to their supercomputer, so that, for example, weather simulations. Here you can sort of see a hurricane simulation about to hit the coast. Streamed directly from their supercomputer to visualize it directly on the wall. At UC San Diego, at the California Institute of Technology and Telecommunication, there's something called the Brew. And here they've taken the approach of creating these things called optic portables, which are these modular tileable display units that fold up nicely into road cases and ship to conferences and so forth. Well, in the room, they basically opened up all these boxes and they set up these displays in a ring and turned this into a giant media-rich meeting room, such as the one that you're seeing in this picture. So you can actually see in the picture the road cases just below each one of the, I think it was like a 2x2 display panel. And these are also now commercial products. And yeah, so the next slide shows Monsanto, which is now heavily making use of this technology. Yes, Monsanto, actually in your neighborhood, St. Louis, Missouri, has one of these systems. They have up to like 4 of these systems now at each one of their research centers. And what they are basically using it for is precision agriculture, doing large-scale genomic data comparisons. And so they're working with us. They funded one of our PhD students in the past to do very specific development of visualization tools for genomic data visualization. They're so inundated with data that they look at just about every visualization tool on the market, and they firmly believe that the future of their field has to be on these large walls where they can compare massive amounts of data. So this is one of my favorite slides. This is me writing my grant proposals. Yes, grant proposals are becoming big data too, especially for larger grants. And so sometimes I'll bring in a team of faculty, and we will have spread out onto the wall, the budget, the solicitation, all the particular documents that we're trying to read and make sense of as we're trying to put the grant proposal together. So for you administrators out there, yes, it's great for writing giant grant proposals so that you can fund buying displays like what I talked about. So I'm going to talk a little bit about K2, and so to transition into that, I want to bring us back to some of the virtual reality technology that we invented in the 90s. So I mentioned the CAVE system, which is on the top left. And then we invented a couple of other lower-end systems like the Immersive Desk and the GeoWall. And then below you see the most modern generation of our tile display technology called the Cyber Commons. Well, we wanted for a long time to be able to merge the ability to show exquisite three-dimensional imagery with the high-resolution capability of these tiled walls. And for a long time it has been either too costly or just impractical. And so last October, we unveiled to the world for the first time something we felt was worthy of the name CAVE. And so we decided to call it CAVE 2. CAVE 2 is the world's first and highest resolution flat panel-based surround virtual reality system. There are 72 LCD panels connected to 36 computers. Now, what's important about it is that not only can you see 3D at extremely high resolution. I mean, when I say high resolution, I'm talking about 20/20 vision. We've never had a CAVE technology that really provides you with that degree of resolution. But in the next slide, what I'd like to show is that CAVE 2 is so much more practical than the original CAVE ever was, because of the fact that you can now display both 3D content and 2D content side by side in a very large meeting room surround space, so large in fact that you can bring in furniture and sit in it and work. And so this now makes it a very, very practical technology. So in the next slide, I'll give you next 2 slides. I'll give you some examples of the CAVE applications of the CAVE. The first one is with a team of neurosurgeons and a professor in bioengineering. His name is Andreas Linninger. He's been doing simulations of neurovasculature for several years. And before he worked with us, he was looking at his data on his regular computer monitor. And when we put his simulation into the cave, and one of the surgeons walked in and looked at the model within the cave, in 5 minutes, the surgeons immediately said, this simulation is actually incorrect. There are errors in the way the branching of these neural vasculature are shown here. And this was an error that was never caught in the simulation for over a year, because using the limited display resolution and also the fact that the display wasn't 3D, it was very difficult to untangle and to really make sense of this. But in this kind of environment, a surgeon who's really familiar with these kinds of structures can immediately see where the errors were. And the next slide shows another really good example of this similar kind of benefit. So literally a month ago, we had a team from NASA Endurance come into our lab and spent 3 whole days in the cave. They turned it into a full meeting room. And the Endurance team is the team that built this underwater vehicle that they sent out to Antarctica to map out this lake that has an ice sheet over it. This is actually a trial before they were to, for example, send out these kinds of same mapping underwater vehicles to other planets. And so in this environment, we used the cave where 1/2 of it showed 2D content. You can see on the left-hand side, the left half shows like 2D images of the map of the lake. On the right-hand side, we showed fully immersive 3D, and each one of those balls, each one of those spheres, is a data point gathered by the AUV. And the chief scientist, Peter Doran, he's actually standing in the center, he's got the joystick. He's flying through the lake because he's cleaning up the errors that the AUV has made in their scans. And the entire lake is visualized in full 1-to-1 scale here. And the reason why this is important is because in that scale, Peter is able to use his intuition as a geoscientist to go in there and say, okay, here's a data point for a supposed part of the lake. I know from my geoscience experience that the geologic structures cannot work this way, and therefore this data point is likely to be an error. So he literally spent hours flying through the space, cleaning the data, and aligning it with 2 different portions of the lake. They tried to do this on a regular computer monitor for about a year before the Cave 2 was built, and it was frankly impossible. It was terribly difficult to navigate through the space to try and see what was going on, and especially without the benefit of 3D. So this is the first case in practically any cave in probably the world where a team has used the cave for a full 3-day-long meeting. And the food is actually, for the meetings, just hanging outside the cave to the rear. So they have desks, they have their laptops, so it's an incredibly practical system. So I'm just going to end my talk with a video, and here's some videos and music will kick in to inspire you of what the cave would look like. And actually go back one slide. There we go. You're going to have to click play. And then after the video, I'm happy to answer questions.